Hello everyone, and welcome to this video in which we're going to be talking about what happens when you start mixing up these gases. And so one thing I mentioned in previous videos is that gases do not care about proportions. Gases mix very well into mixtures. And so remember back from chapters 3 or 4, mixtures will mix or will combine in any and varying proportions. And so one of the good examples I gave for mixture was air. And so depending on where you're standing, you're going to be breathing in, again, quote unquote, different air. But we call it air if it has all the same characteristics as all the other air we've ever breathed in our life. But depending on where you're standing, you might have a different proportions of those gases that make up air. And so the proportions of CO2 to H2O to O2 to N2 to argon to all the other gases that compose air will be different if you're standing inside of your office in your house, or if you're standing outside on a nice sunny day, or if you're standing in the Antarctic, or if you're standing on top of Mount Fuji. You'll have different proportions of O2 to H2 to CO2 to N2, and you see where I'm kind of going with this. So gases mix homogeneously in any proportions. But because of that, there are going to be different gases contributing different pressures depending on, again, what kind of mixture or what kind of proportions you have there. And so we refer to these different pressures contributed by different gases as partial pressures. And so Dalton, the guy who started talking about marbles way back when, he came up with this whole idea of partial pressures and total pressures. And so Dalton stated that the total pressure is going to be equal to all of this partial pressure sums. And so if you have a sample of H2O and N2 and O2, depending on, again, how much of each of those proportions there are inside of that mixture, different gases will be applying different pressures to the inside of that container. And so if you know something about the moles, or again, something about the amounts of each of those gases, you can determine what they call a mole fraction. And so a mole fraction is nothing more than the amount of the substance you are talking about. In this case, I call A. It's going to be the amount of A over the total amount of all of your gases. And so a mole fraction, very similar to any of the other fractions we've talked about in the past, is just the moles of whatever you're looking at over the total moles of all of the gases included. And so if you want to know the partial pressure of gas A from the total pressure, you just need to use the mole fraction of A times the total pressure will give you the partial pressure of just the gas A. And again, have a few examples kind of coming up here in a second, so don't give up on me yet. And so this next kind of concept makes it a little bit less confusing because I found this picture that helps kind of explain what I'm trying to talk about here. So normally, if you are going to collect a pure gas sample, it is very difficult to do in the presence of atmosphere, like the stuff we're standing in all the time on planet Earth. And so typically the way that this happens is you either have a liquid or a solid inside of a test tube, and then you actually have a silicon tube or rubber if need be, kind of attached from this tube going under the water up into a flask or into a beaker. And so normally the way that this is initially set up is this beaker is completely filled with water, and so filled all the way up to the top. But as soon as you start heating up your sample, and again, the solid or liquid is converted into gas, the gas travels down the tube and bubbles into the water here and starts, again, filling up the top portion of this container, which displaces the liquid further and further down. And in this situation, now you have gas that has not touched any of the atmosphere that is surrounding it, so therefore actually hasn't been contaminated. The only problem with this is water, it's kind of thinking about it like water has Velcro on its hands, on its hydrogens. And so as these gas particles start bubbling up from inside the sample and start filling up the inside of this container, some of the water kind of snags on along and kind of holds on as it rises up here. And so it's a very small portion, but again, some water does go from the liquid state into the gaseous state. And you can kind of think of it as Velcro kind of holding onto these bubbles And so as it breaks free from the water, some of the water, again, kind of quote unquote, leaches on and sticks to these other gaseous particles. And so the issue with that is whenever you start talking about the pressure inside of this container now, or the pressure of gas inside of this volume inside that like been displaced, most of this pressure comes from the gas that you are forming. And so again, gas coming in from here, going down this tube, and up here as pure gas. But as soon as it breaks through the surface, some of the water attaches to the gas, and so some of the pressure inside of here is also coming from gas molecules that, again, dissipated from whenever it was a liquid. And so anytime inside of your problem, if you see this term, vapor pressure, then you automatically should have a red flag go off in your brain saying, wait, the total pressure is going to be a combination of two different things. The total pressure inside that container is going to be the sum of your pressure of your gas that you're interested in, plus any vapor pressure, pressure of water that kind of came along and tagged along with this gas whenever it broke free from the water. Great thing about this is your vapor pressure is going to be only dependent on the temperature of the water at which point you are collecting the sample. And so in this situation, vapor pressure must be given to you. I will have to tell you in the word problem the vapor pressure of water at this temperature is blah, blah, blah. One thing I've seen a lot of students just kind of either glance over or completely ignore is whenever I say something about vapor pressure, you need to account for the vapor pressure out of the total pressure. You can't just glance over and ignore it because, again, the pressure given to you is going to be the total pressure. It's going to be the pressure of the gas plus whatever pressure of the water that's involved inside the situation as well. Like this particular practice problem right here. And so I have acetylene that's produced in the laboratory when calcium carbide reacts with water. And so I give you a balanced chemical reaction here in which you have your solid calcium carbide interacting with liquid water. Please notice not aqueous, but liquid water. But whenever this happens, you produce a gas and you have some aqueous calcium hydroxide as well. And so when you kind of go through and look at this, a collected sample of acetylene has a total gas pressure of 738 torr and the volume of 523 milliliters. At the temperature of the gas, the vapor pressure of the water is 21 torr. And I want to know how many grams of acetylene are going to be collected. And so as I mentioned, the key term you should be looking out for these particular questions is the vapor pressure. Or if I say anything about the pressure of the water at this temperature, you need to remember that this term up here, total pressure, is no longer the pressure of just your gas. The total pressure is going to be the pressure of both your gas and of the water that is being kind of sucked out whenever this thing escapes from, or whenever the gas escapes from the water. And so narrowing everything down here and picking and choosing my fun stuff, I know the total pressure. I know the volume. I know the temperature. I know the vapor pressure. I'm looking for the mass, and so come wipe all this clean, keeping the important stuff here. Total pressure, volume, temperature, vapor pressure, and we're looking for the mass of the acetylene. And so we'll take care of pressure here in a second, but as I've mentioned several times, and hopefully I sound like a broken record, because that's the only way you're going to get it into your brain sometimes, volume must be in liters, so convert your milliliters into liters. Temperature must be in Kelvin, so make sure to convert your temperature to Kelvin. And the last thing is, total pressure is not what we're interested in. Vapor pressure, also not what we're interested in. Because we're talking about a volume of a gas, the temperature of the gas, most likely the useful thing here is going to be the pressure of just the gas. And so if we want to know the pressure of just our acetylene, we would need to take the total pressure, subtract the pressure of water from that to give you just the pressure of the gas. But as I mentioned again, several more times, pressure needs to be in atmospheres. And so using the conversion of 1 atmosphere equals 760 torr, torr will cancel with torr, and now we're sitting at pressure. And then from here, we know P, we know V, we know T. We're always going to know R, And so, as seen in the past, the only unknown situation here is going to be our moles. And so just rewriting the equation of moles equals PV over RT, we know the pressure in atmosphere. We know our volume in liters. We know R is going to be in atmosphere liters per mole Kelvin, and we know our temperature in Kelvin. And so here we have atmosphere canceled atmosphere, liters canceled liters, Kelvin canceled Kelvin, and our only unit left over is going to be in terms of moles. And so the last question that's actually being asked here is, how many grams of acetylene? But luckily for us, we know the chemical formula of acetylene, so we also know the molar mass of our acetylene, or you can solve for the molar mass of acetylene. We have 2 carbons, so 12.01 times 2. We have 2 hydrogens, so we have our 1.01 times 2. And so a 24.02 plus 2.02 will give us our 26.04. Convert moles, cancel out moles, and our final answer is left in grams. And so, as I've mentioned several times by now, these problems may seem long, they may seem tedious, but all you need to do is isolate your pressure, your volume, temperatures, and or moles, depending on what you're solving for, and make sure they're in the correct unit. After that, just another plug and chug. And this last step, converting moles to grams, we've done this many times, so this should not be scary part. The only real scary part here is, again, figuring out what they're giving to you, correct the units in terms of atmospheres, liters, and kelvins, and after that, it's just a plug and chug. So speaking of grams and moles, something that you should probably kind of have guessed was coming up from the title of the video, stoichiometry is back. But luckily for us, stoichiometry never has changed. The whole idea of stoichiometry still just goes back to, if you have a balanced chemical equation, you know the relationship between the moles of A and moles of B. And so all I'm really doing here is expanding your vision. And so when we first began, we went from mass to moles to atoms. And then once we introduced the balanced chemical equation, then we were able to go from mass to moles to moles to mass to moles to atoms. And then we threw in molarity, and then now we're going from volume to moles to mass to moles to volume to moles to atoms. And so the next thing I did is just threw in another relationship between moles and 3 other variables, like pressure, volume, and temperature. And so now if we know pressure, volume, and temperature, and we're given a balanced chemical equation, we can go from pressure to moles to pressure to moles to volume, temperature to moles to grams. It's just the same exact recipe, we're just changing up how, the order in which we're kind of dealing with this stuff. For example, what volume of H2 gas at 765 torr and 225 degrees Celsius is needed to reduce 35.5 grams of copper 2 oxide to form pure copper and water? And so the first thing you should probably notice about this particular question is I'm asking about the volume of H2. I give you the pressure of this H2. I give you the temperature of this H2. The last thing is I give you mass of copper oxide. And so if you want to use PV equals nRT, you have pressure, whoop-de-doo. We have temperature, awesome. We are looking for moles, and so again, we can't have more than one unknown variable there. And so if I give you information about copper 2 oxide, but I want to know something about volume of H2, at some point, you're going to have to swap between the two. And so in order to do that, you need to have a balanced chemical equation. And so once you have the fact that copper 2 oxide, remember, this needs to be CuO because copper's a 2+, oxygen's a 2-. This is the only way you can have a 2+ and 2- cancel each other out. H2, hopefully you know that by now. Additionally, I tell you pure copper, and hopefully you know the chemical formula of water. And so now we see that this is a 1-to-1 relationship, meaning the fact if we know the moles of copper 2 oxide, we also know the moles of our H2 gas. And from there, make sure all of our units are in their correct form. We know that torr, not going to do us any bit of good. So we need to make sure our torr is converted into atmospheres using the conversion of 1 atmosphere equals 760 torr. And again, Celsius, not going to do us any bit of good, so we need to convert our Celsius into Kelvin. And so here I just kind of dropped off the 0.15 because at this point it's a little bit excess. And so here the 225 plus the 273 gives us 498 Kelvin. And so we know our pressure, we know our temperature, we're solving for volume. Again, all of this in H2, but we don't know moles of H2. And so if only we had a way to figure out moles of H2 from a given complex, maybe something like 35.5 grams of copper 2 oxide, and using a, again, balanced chemical reaction, we can figure out the molar relationship between our copper 2 oxide and our H2 gas. Using the molar mass of our copper 2 oxide, which again, you either have a periodic table or this will be given to you in one form or another, we can solve for our moles of our CuO, so therefore we can solve for the moles of H2. And so using the balanced chemical equation here, using the given information, 35.5 grams of copper 2 oxide, using the molar mass of your copper 2 oxide, we know we can go from grams of copper 2 oxide to moles of copper 2 oxide. Using the relationship of one of these guys gives you one of those, or reacts with one of those, we know our moles of CuO into moles of H2. And now we know moles of H2, we know pressure of H2, we know temperature of H2, the only thing we don't know is volume. And so rewriting PV equals nRT, we have volume equals nRT over P, moles we just solved for. R is never going to change. Temperature, change into Kelvin, pressure, change in atmosphere. It's just another plug and chug problem. And so I understand if this seems repetitive and like I keep saying it over and over and over again, but these problems are not as difficult as your brain is going to try to make them, especially when it comes to like these dimensional analysis and the stoichiometry. We've done many examples of this. We know how to convert from mass of a substance into moles of something else. The real issue here is just making sure that your pressure is in atmospheres, temperature is in Kelvin, your amount has to be in moles, and then that's it. Just plug and chug.